Okay, my friends, I'm going to start it off by saying that CERN is trying to find these electron neutrinos, electron showers, by exploding protons together, which are thousands, tens of thousands of times bigger, and then sorting through the debris. Rodney Warren and I are doing the same experiments, only we're using light to start with, so we can actually see what CERN wishes they could see. I know it sounds absurd, but here it is. There's your electron neutrino showers. This is coming at us, high-speed electrons, exactly what they say, creating these fields. Now, let me just show you a couple things of whet your appetite, and then I'm going to go into extreme detail. Coming out of there was a mini disc, and it smashed into this. It created whatever that is, which all the other light did this. All the other light, you see it right here? They all came out in these Higgs fields except that. That's the one that crashed. Now, look at this. This is extremely interesting because this is all red light. This is all red laser. Should not be changing colors. That's what really's got me a little perplexed. Because as it comes out of here, look. This is on the move. You can actually see them moving. You see that? You see this one, the blue? That shouldn't be there. They should all be red. They should all be red. But I see why it's there. It's being crushed from both sides by fields impinging on it, squirting it out like a cork. It changed its color into a higher energy color, blue. It elongated the field. See how these are little flat looking fields? This one, it went flying out, and now it's starting to compress back again, and it will change back to red here. So I know that the actual light of red can change its frequency, and then it appears like it will come back to its original frequency. There's a lot of work to be done here, but this is very serious stuff. We started with red light. Nobody can say anything different. There is not a person on the face of the earth, and I know that that was red here, and it turned blue because it's crushed. So we know that the frequency, which the particle actually, see that little dot right there? That's really the particle. It's spinning so fast that everything around it is showing up excited in a field. And so this is what's coming here. Now, here it was here, like this. When it got into that blue state, it has to be like this. Because that's what blue is. Red is way down here. And blue is like this. And then it's popped it right out. Very exciting stuff. But Rodney is the one that should be getting a Nobel Prize for this. He's absolutely phenomenal, and the amount of work he did. And this goes back, I don't know, 4 or 5 years. That was from just recently that I just, that one, yeah, he just gave me that a few months back. But it goes back to 2016, and that was at the end of the work cycle, so I don't know, in May 2016, 4 or 5 years ago. But absolutely amazing work. When I saw what he was doing, I blew my mind. Because look at this, look. This is green, same thing. It's coming out of here, real high speed, and then they start to slow down, and then they become visible. But it's the same particle, you see it? The same particle. You see the spikes coming out of it? As it concusses, it's like boom, and you're getting energy spikes coming up the bottom, and then it gets a little blurry, and then it sort of flattens out after a little. Well, there are always only 2 cycles I've ever seen, only 2. And here's a real close-up. You see it? Here's those spikes. And that's on the first concussion. On the second one, you maybe get a little, and it starts to come down like this, because when it's hitting, it's pushing it open. It's bam! It's like a ball opening up, and the spikes go up. I got a ball around here somewhere. I was showing. Here. It's just like this. Only consider this is a region of polarities, positives and negatives. But when it slams into stagnant air, which also has molecules in there that are electrons, the whites are going to oppose them. And it's going to go like that. And you're going to shoot up here and shoot down here. It's going to flatten out. and then as it slowly comes back to less acceleration, it'll come this way. And that's exactly what we see. Identical. Okay, my friends, it's Roger once again, and I have absolutely amazing news. This is stunning. This goes back a couple of months, back to December last year. New boson appears in nuclear decay, break standard model. Well, nuclear decay means they got big nucleuses smashing together, and they see all of this debris like this here, and they're looking for a boson. Okay, so here's what it says. Weird electron, positron, decaying beryllium and helium hint at new boson. Well, boson is like the tiniest particle there is. And see all this stuff? They're hunting through all this to find a boson. And here's what it says. This is a collision at, CERN, the Large Hadron Collider. Compact muon solenoid detector produces a Higgs boson signature. Well, they're the round things. We'll look at them. Now, in the world of physics, nothing gets the blood flowing like the thought of a new particle has been discovered decades. New physicists have been hunting for evidence that modern physics isn't right, which it isn't, and the smoking gun has remained elusive. Now, in November of last year, people started polishing a Nobel Prize. I hope they got Rodney's address, for a group of physicists who seem to have found the new boson. Wow, that's amazing. Rodney found it a long time ago. A new boson means a new force, which is even more exciting. Is that gun smoking yet? Well, yeah, it's been smoking a long time, 5 years. They knew this 5 years ago, but nobody could ever show it or prove it. And I got to be honest with you, I think the only reason they're starting to fess up now is because Rodney showed it. I'd like them to show me theirs. I don't think they can. And I can show you that we're not working with gigantic particles to find the smallest particles. We're already working with the smallest particles, and we can see them. And I can show you the bosons, and I will right now. And not only that, let me show you what the Royal Institute says, Royal Academy Institute or whatever they are over in London, the big shots of the world. Got 760,000 subscribers in Geekland, so you know they're the biggest guys in the world. So let me show you that. Okay, once again, they just announced this a few months ago. This is the Royal Institution, 770,000 subscribers in the land of geekness. And here's what she's got to say about lepton universality. I'm going to explain to you all the particles. It's kind of funny, actually. Okay, here we go. She's going to be talking about why the standard model is wrong. Here she goes.
Lepton universality seems to be violated. Well, what that means is that there's something wrong with the standard model. We found the crack, finally, in our understanding of particle physics. There's absolutely no way that we can explain this observation with our current understanding. In fact, the only way we think we can explain what's going on is if there are new particles in the universe associated with new physics processes beyond those that we understand, and that these new particles are interfering with the
B mesons as they decay. Well, let's talk about that. They think there's new particles because they can't get it through their head that there is no protons, there is no neutrons, there's nothing but tiny particles that make everything. They're called electrons. I'm going to show you that in great detail. This is where they just can't get past the fact Einstein was wrong, Hubble's wrong, Bohr is wrong. Well, they know Bohr's wrong, but they think that there is some other particle that Bohr just missed. Well, he missed everything because everything's made out of these. So they got a particle that's like this somewhere that bangs into something and interferes with the B meson decaying. So what? It's 25 of these instead of... You know what I'm saying. Okay, watch. All right, this is particle physics. B mesons composed of bottoms, antiquarks, and all these things. And it's really funny. It gets crazy. Look at this. But rather a bottomonium, which is something else entirely. You're not kidding. It's just unbelievable, the names they come up with. It's hilarious. Wait till you see this. The list of particles. I'm going to show you the list of my particles in electron flood theory, which is all electrons. All right, here's the elementary particles. Elementary, but you're not kidding. So now they're coming up, because you can see all these different charges. Absolutely, they're there. But that doesn't mean there's a particle for every one of them. They're just doing different things at different times. Watch this. Electron neutrino. Where do you see this? Electron showers and electron neutrinos. They think they're just the most mysterious things in our world. Then bosons. Bosons are one of the two fundamental classes of particles, the other being fermions. I'm going to show you both of them. And they are both built into an electron. And here I go with photons, absolutely. And they have no charge because they're back-to-back charges. All right, so there's one here, and there might be one over here and one over here, but it's like a complete uniform box of charges, so that there's really no center of charge. There's no dipole moment here to speak of that I can think of. There's just a scattering of magnetism that surrounds this. And that's what I'm considering a photon. Now, look at all these things. Graviton. Graviton is all of these things they find in all of these different particle-looking things, and they assign it into a particle, but it's just not. It's just bigger or smaller pieces of the gigantic mass. And they go on and on and on. I mean, the guesses are absolutely stunning. So now I'm going to show you my theory. Okay, I say everything is made out of electrons. This would be a proton. It would have stability at 1838 of these particles. It would be and get stable. 1837. 1838 is a neutron, but it's just going to float between those two states. Now, you keep adding more and more neutrons and protons, you keep getting bigger and bigger molecules. 100%, I mean atoms, 100%. And then these atoms will attach to other, but their atoms are big, gigantic chunks of these, thousands and thousands and thousands of particles, where they have a couple here and 8 or 9 here and 20 over here and 50 over here. We've got 20,000, 50,000, 100,000. Every electron is 1, and every proton is 1837, and every neutron is 1838. That's the land of electron flood. And here's the electron flood theory list of particles. This is all the particles there is. There's electrons, and that's it, case closed. They have a weak and a strong dipole, a black and a white, and I'm going to show it to you. Photons are, like I say here, back-to-back electrons. There's the weak and the strong, but they're grabbed together with other ones in a box. Stable electron masses make atoms. That's these, when they get stability. And they're always shaken, they're always in motion until they hit a certain frequency. And then they lock in. And then they lock in. And they lock in up there. And it's the vibration of the particles in the mass that creates stability. And each one of those islands is stable. That's what we call atoms. Atoms together, you take a couple of these together, and they have little things sticking out of the ends of them. And some of them will go like that and say, oh yeah, you can come over here and we'll stick together. We'll share those electrons. That is called bonding, and that is called molecules. Right? So those are the molecules. And gases in the air are molecules. Water is molecules. There's little pieces and bits floating in them. Those are molecules that are grouped together in their own little universe with inside these fluids and airs and all that, and there's a bunch of molecules in here. Well, there's some groups of molecules in the feathers of this goose's head that are different than the eyeball of this goose or the beak. Even though we're looking at them here, they're very similar looking. If you broke that down to its components, there will be differences in the actual electron masses, which we call molecules. And the matter will be a bit different, but matter is matter. It's balled up particles. You know, the complexity that they have made everything into is just, it makes everything into nonsense. Okay, these are some shots done by Rod Warren. I worked with Rod, 4 or 5 years ago on light acceleration experiments. Now, he did the actual experiments. I do the theory, the electronic theory. And Rod came up with this, not searching for the speed of light or any of these particles or anything. He just happened to run across it in a general experimenting. Nothing fancy, just a guy trying to learn what light does and seeing these experiments, trying to verify them. And that's what I do. I try to verify everything. So here he does. He sends it through his Venturi. And here, let me just show you the Venturi first of all. And then these are the particles that we can actually see. And those are the photons that I chose, just like this. We're going to be looking at them in a minute, and I'm going to be looking at them how they react, and because I got a lot more to show you. But what we had here, all Rod did, and I did the same experiments here, but nobody can beat Rod. Red lasers, this exact same red laser, a Bosch GLM 15. It's a pulse red laser. Bip, 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 bip. It makes these things, and then they bounce back and they receive it. We don't care about the receiving. We want the pulse of the red laser. So then what he did, and it was very close to this, he made some little device in, I'm not sure. You got to work with Rod on this. This is his baby, but I'm just going to sort of explain it to you. He made something that looked like clay or glue or something like that, and then he put two nails side by side out here as the Venturi. Okay, so that light has to come out of here, and because when it comes out of there, I'm not kidding you, it comes out this big. I'm not kidding you, it comes out gigantic. Light is huge. You don't see it because there's a dot, and I'll show you the dot that's in it. That's the dot. When that dot comes out, it owns a field around it, absolutely enormous. And he made it forced into those restrictions, which made it shoot just like a hose, just water out of a hose, almost identical. So what we were looking at was photons coming out of here, bip, 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 zzz, and then they go flying. And when they hit here, these particles separate. That's the boson. One of these is a fermion, and the other part is a charged particle carrier, which is called a boson. And the two of them together make an electron. I'm telling you, I'm going to show it to you, and I can literally prove it. Let them prove it. Now, here's what happens. The photon comes out, beep, 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 zzz, because it's got to speed up to go through here. When it comes into here, there is so much chaos, and because the charged carrier, this is a carrier, there's no power. There's no power. It's a weak force. It just rolls away. And the powerful part explodes like an atomic bomb. This is a Venturi single slit. It creates the interference patterns behind here because they're not waves. They are spinning particles. Hold on. Oh boy, where is it? I can't find it. Oh boy. Hold on a second. Okay, sorry about that. So here's this red laser. It's not coming out like a big pulse. It's coming out like this particle. And that particle is actually spinning, just like this. And I'm going to show it to you. You'll see the spin. You'll see all that. Now, so here we have the photon. If you split the two of them, you have an electron. When they concuss, you have this. The red, which in the case of these things are white, but explodes like a bomb. The black just rolls away. This is called concussion separation of charges. Here is the actual physical proof. Physical, actual proof. Those are the electrons, the photons I was talking about. Split them in half in their electrons. Break the white from the black, and you have charge separation and the boson that's going to get Rodney his Nobel Prize. So there's a high-speed electron creating electron-neutrino electron showers. We can do those all day long. All right, so here's your red laser creating that. This is where the field starts to pull, and your particle becomes visible. which it is a particle. You see this? There's the particle stream right there being pulled away from the wave. So it is a particle, and then it shows itself. It's obviously accelerating. Einstein was wrong about that. It is a particle. Everybody was wrong about that. It is going through a Venturi, which is right here. And this is a single slit, and it creates interference patterns. Everybody's wrong about that. This is the concussive electron, the strong force of the electron, the negative. And the black ones are all around it, and I'm going to show you that in a second, which are the separated charge carriers, the boson we're looking for. Now, what do we have here? Those are Higgs fields. This is coming out of the accelerator towards us. They're spinning like crazy, creating these polarized fields. And there was one little tiny white particle up there that was spinning backwards, and that concussed over here, creating a particle nobody has any clue about. See it? Boom, boom. It hit this field here and created a ghost field. See it? And that, whatever that is, je ne sais pas. Now, what do we have here? These are our photons. When they bang, you can actually see spikes come out. We got them in green too. And then they sort of flatten out, and then over here they just sort of flatten out like this. You don't see them anymore. The only reason you can see them is because they're accelerated at that point. And I can tell you, there's no question these things are accelerating. You see that? That's the light coming through. It's accelerated and slowing down there. It's spinning like crazy. And that means it's drifting to the right, spinning to the, you know, spinning to the right, drifting to the left. Now, I'm going to show you the bosons. Polish up that Nobel Prize. Okay, don't forget my wonderful, energetic friends. Here comes our particle. Boom! It's got to accelerate. It's fighting all its neighbors. The black guys say, you guys can fight it out. I'm just going to wait around the edge. And they do. They go around the edge, and then they come back to the explosive, energetic part of the electron. Because coming through here, this is a photon. It's light. I mean, I don't care. Nobody can say anything different. It's a light. It's coming out of a red laser light. And the thing that drives me absolutely up a wall is for all of the top physicists that I've contacted, oh, that could be anything. And then they just stop contacting. They don't want to talk about it. There's no interest whatsoever. I even took a course at the University of Geneva, Switzerland. I guess it's in Switzerland. I don't even know where it is. It was an online course. And they were thrilled. Oh, yeah, that's fabulous. That's amazing. I said, well, let's talk. Nope, don't want to talk. It's okay. It's amazing how little will ever get transferred to anybody because nobody wants to talk about anything that they have. It's going to upset their apple cart. Very distressing. So don't forget now, polish that up. I'll get Rodney's address for you. He can just blow these things off anytime you want. You want some more electron showers? Hold on, I'll get you some more. You see that right there? This is a Samsung Galaxy 3 or whatever it is. That's it right there. You see that? That's a Bosch GLM 15. Red laser, pulse red laser. Now, I don't happen to have any nails with me at the moment, but between the three of those, that's the entire amount of equipment that Rodney used. You know, I use the same thing here, but again, you can't be Rodney. You want to try to be Rodney? Good luck. He sent me more pictures you just couldn't even imagine, and they were every one of them. Just blew my socks off. Now, so now, here we go with CERN. They got a little more equipment than we have. You know, they probably, I don't know, some Rodney, I forget what it cost me. I guess maybe $100, $200, I don't know. But I guess they spent a little more money than that, and they created basically the same thing. You see these circular patterns? Well, all matter is going to create the same look, and they're just bigger chunks. So when they come here with two huge particles, bam! Now, what comes out of there isn't every one of them doesn't come out, a single one. And that's what they're looking for. And Rodney and I had the singles. Now, what are they seeing? They're seeing some of that. They're seeing some of this. They're seeing some of that. And then they're trying to find one of these out of all of that mess. Well, we started with one of these. We have no mess. We have fastidious, magnificent, exquisite particles that are totally easy to see. So, if CERN would like a little help, I suppose Rodney is willing. I'm willing, you know, I'll help him. What the hell? All right, I love you guys. You're doing a great job over there smashing your protons. All right, Vios con Dios amigos.